Alright everyone, welcome everybody to the video. Today I'm explaining like the main Dijkstra's algorithm. Okay, Dijkstra's algorithm, what it is. So Dijkstra's algorithm in short way, it's like finding the shortest path between two vertices of the graph. And let me show you. Here I know it's a very different way of representing things, but I think it's good. Hold on. Let me see if I'm recording everything. Yeah, everything is good. Oh yeah, sorry you guys. Yeah, so basically if you take a look at this A, B, C, D, imagine it as a vertex. Okay, just imagine it as a vertex. So I have point A, B, C, and D. So as I told you, Dijkstra's algorithm is like shortest way from A point to the B, or from one point to the other. Yeah, from A to B and C and D. So Dijkstra's algorithm says, in theory, if you want to go from A to D, the shortest path is going to be like the shortest path available. Not this route, for example, yeah? Not like this or that. This way, and then go down to go to C, and then go to D, okay? So yeah, this is how it's gonna work. And when you do that thing, it's important to understand that. So when you are going from A to D, the shortest way is going to be like this, yeah? Because it's like you take the shortest routes and paths. And it also means that when you are going from B to D, the shortest path between B to D is gonna be exactly the same one, like subpath is the same exact subpath between A to D. It means like when you go to B to D, you should pass through B to C, and then from C to D, it's gonna be the same. So this is basically what I like the main of this Dijkstra algorithm. Okay, let's go on into the program. So right now what I'm gonna do is, first of all, I'm gonna summarize that one more time. So it is, as I explained earlier, it is used to find the shortest distance from one starting node to all the other nodes in a weighted graph with non-graph edges. So let's start out with the code though, okay? Import Java util. We are just in this program, it is mainly used for arrays, fill and arrays string. So we are just printing the distance of array, yeah? And then next, immediately, we are defining the class of Dijkstra's algorithm, yeah? So how we are defining class, everything related to the algorithm is implemented inside the class. So the next line is gonna be representing the max value. Here, this content represents infinity, yeah? An important thing here to understand is that since Java, like Java interface, does not have inbuilt infinity value, what we are going to do is value for integers. At least we use the maximum possible integer to represent a distance that is known that is not yet known or unperceptible. So we, instead of infinity value, we are going to use this max value system, yeah? Moving on, we talk about methods, like, right? As we go along, we are using like the 2D methods for two parameters, like public static void. We also use this public static void in other Java programs we have discussed it so far in other videos. So we are gonna be using the same kind of code here. Yeah, the first is a 2D array. It's also called graph, which it represents like the adjacency matrix of the graph. Yeah, the second one here, the second one is start, which is the index of the starting node. So here we are representing, yeah, int graph length. So we are representing like the distance of the graph, yeah, here. All right, moving on. uh, so, well, Let's take a look one more time. Is everything correct here? Let me just do this one more time. Uh, so yeah, as we move along, we see, hold on. Ah, that was the reason, you see. Like there was like the stop. That's why, you know, I couldn't see the other values being represented. So I'm gonna run them one more time, but for now I need to explain what is between these codes, yeah? So let's start from Boolean, yeah? Here we are explaining like adding new Boolean value. This array tracks whether a node has already been finalized or not. Once a node is marked as visited, its shortest distance will never change again, okay? It's not gonna change anymore. Next, we are initializing like the fill statement, right? At the beginning, all distances are unknown, so we set them to infinity. It's important, yeah? So especially and specifically in Dijkstra's algorithm, it's important to understand that if there is something unknown, if you don't know something, you just set it to like infinity, okay? This is how you're gonna deal with it. Then distance start is gonna be equal to 0. The distance from the start node to itself is always going to be 0. Now we enter the main like for loop, right? As we are doing all the time. This loop runs n minus 1 times because this loop runs n minus 1 times because each iteration finalizes exactly one node, okay? Inside the loop, the first line is this line, yeah? So this 15th line, this basically selects the unvisited code, like node with the smallest current distance. So this is what it's gonna do. This is what we call as the greedy step of Dijkstra's algorithm, right? Interesting fact here that I should mention. Uh, if this step is implemented using a priority queue instead of a linear scan, the algorithm becomes much faster for larger graphs. So it's going to be faster, yeah, working much better for large graphs. This version is simpler but slower. This is like, as you remember from older videos, we had like main Java. We had like insertion sort, which was working pretty nice for small codes, but for larger ones, there was like genetic ones that was working nice. So the same thing is gonna apply here. So the larger it is, the more comfortable, complicated it's gonna be for it. So it's much better for smaller values, right? This complexity of OV. All right, then we are marking the chosen node as visited here. We are marking the node as visited, meaning its shortest distance is now fixed. Yeah, we are fixing the shortest distance between them. Now we check all neighbor of this node. So with for loop, we are starting out. This loop goes through every possible node to see if there is an edge from U to V. The condition inside the loop goes on in that way. Here it is checking four things, okay? Four things. First, it's gonna check whether the neighbor hasn't visited yet. Has he visited yet or not? It's gonna check. Second, it's gonna check there is an edge between U and V. Yeah. Third, the current node is reachable. Fourth, going through U gives a shorter path to V. This is what it's gonna check. If all conditions are going to be true, we update the distance to distance v is equal to distance u plus graph u and v. So this step is called relaxation. It means we found a better path. Another interesting fact I should mention here is that if you ever add a negative edge weight to this graph, this algorithm can give wrong results. Dijkstra only works correctly when all edge weights are non-negative. You see, non-negative. You're gonna have to remember, because like when you are doing it, I also did it with like the graph. The value can never be negative, right? Because like it's distance. Like if from geometry, you might know like the values are never negative. After finishing all the neighbors, the loops end, and eventually we print the result. This prints shortest distance from the starting node to every other node. Now we have to move to helper method, right? So we are printing out the shortest method, and then we are moving on to the next one. So this method here finds the index of the unvisited node with the smallest distance. Inside it, we define int minimum is equal to infinity, min index is going to be -1, min stores the smallest distance found so far, and min index stores its position. All right, we loop through all nodes again. For loop, as always, using if a node is not visited and the distance is smaller than or equal to the current value, minimum, we update it to minimum distance I. And yeah, basically that's about it. And we are also at the end returning the value. This gives the next node to initialize. Interesting fact, one more time. This means that in case of a tie, if it's a tie, right? If it's equal, the later index is chosen. This doesn't affect correctness, only which valid shortest path is chosen. Finally, we are reaching the main method, right? Finally, we are on the main method. Here we define the graph as a 2D array, right? It's in the 2D version. And each row of here represents a source code, a source node, each column a destination node. A value of 0 here means there is no direct edge. After defining the matrix, we call Dijkstra graph 0. 0 means no value, okay? This runs the algorithm starting from node 0. Interesting fact, one more time here, if you change the starting node here, for example, from 0, if you change it to 3, the algorithm still works, but all distances will now be measured from node 3 instead. So we don't want to do this, and I have the 0 itself back. There we go. Perfect. And now that completes the program. In summary, this code repeatedly chooses the closest unvisited node, locks its distance, and updates its neighbors until all shortest passes are found. Let me run this program one more time to see if everything is making sense. Okay. I think. Wait. So if we delete this and run it one more time, it should be working, right? Yeah, I'm sorry for the machine. It's gonna take a little bit of longer time than usual because my machine is not the best, but it's gonna be fine, I guess. So yeah, I believe it's gonna take the same type of result. Yeah, 0, 4, 12, 19, 21, 1, 11 should be the same. Yeah, as you can see, it's like compiling just like the way it is. So yeah, basically, I think you got the idea. Dijkstra's system, like algorithm, is basically that. Thank you very much for the video, and see you around.